Okay, so chapter 8, rotational kinematics. We already talked about kinematics in one dimension and two dimensions. Kinematic describes describes the motion of an object. Motion of an object. So we talk about objects uh, on one dimension, two dimension. We learn how to calculate the distance, displacement, velocity, acceleration. In this chapter, we going to talk about rotational kinematics. What is rotation? Rotation describes uh, every point in an object uh, moves in a circular path. So every point in the object every point in the object moves in a circular path. So if you consider a sphere and if it is spinning, so every point on this ball moves along a circular path. Every point moves along a circular path. So we're going to talk about rotational kinematics under this chapter. We're going to talk about distance or displacement, velocity, and we're going to derive equations for all these variables, and we have specific names for these different variables, and we'll talk about in next few slides. Okay, here's an example of simplest kind of rotation. Points on the rigid object. Rigid means the points are not moves. Uh, all these points move around this axis with respect to each other, and an object that retains its overall shape. So whether it's rotate or not, all these points intact. So it retains the original shape, whether it's rotation or stay at the same position. So that's the simplest kind of rotation. It just rotate around one axis. So there are other types of motion. So it rotates and also it translates. So it's a combination of rotation and translation. So it moves. In addition, it spins by itself. All the variables we going to learn in this chapter are very similar to the previous chapters we learned about one-dimension motion and two-dimension motion. So we talk about displacement. So if you talk about a linear motion, displacement between 2 points is x, final position, initial position. So displacement, we use delta x, change of position, which is equal to final position minus initial position. So in rotational motion, similar to, we have an initial position and final position, theta and theta naught. If it is rotation this way, so this angle is delta theta, which is equal to final angle minus initial angle. Very, very similar to this equation. Delta theta, change of angle, which is this angle, is equal to final position minus initial angle. Final angle minus initial angle. So if the initial angle is, if this angle is 90, So, simple example. So angle change is again final angle minus initial angle. Very similar to linear motion. Uh, Change of position is equal to final position minus initial position. Here we talk about angular, so therefore final angle minus initial angle. Okay, so linear motion, displacement delta x equals x minus x naught, and the unit, SI unit, is meters because distance SI unit is meters. So delta theta equals theta minus theta naught. It's an angle. Therefore, SI unit, we know angle we measure degrees. But SI unit is radian. We use rad, R-A-D. Uh, and 2 pi radian is equal to 360 degrees. So this is the relationship between degrees and radian. So 2 pi radian is equal to 360 degrees. So in this slide shows how to convert degrees to radian. So theta equals this length divided by the radius, this angle. So I'm not going to talk in detail, so you can check. So this arc length is 2 pi times r divided by the radius r, which is equal to 2 pi. So 2 pi equals 360, this angle. Okay, now we're going to talk about angular velocity and angular acceleration, just like linear velocity and linear acceleration. So we already talked about the displacement. Angular displacement is equal to final angle minus initial angle. Okay, so average angular velocity, we use omega, is equal to angular displacement divided by the time change. So delta theta of equal divided by delta t. So in a, in a linear motion, we talk about acceleration. We use a, linear displacement, x minus x naught over t minus t naught. Here, angle change, which is angular displacement over time. So the unit is, we already talk about the SI unit of angle change, which is radian, divided by the time change, still seconds. So radian per second. We talk about instantaneous velocity, which is v equals limit delta t tends to 0 delta x over delta t, instantaneous velocity. So similarly, we can talk about instantaneous angular velocity, the velocity of an object rotating around itself or about its own axis. The velocity at a given point on the surface at a given time, we call it its instantaneous angular velocity. The next topic is angular acceleration. So we already learned acceleration is velocity change, final velocity minus initial velocity, t minus t naught. So velocity change over time change. So here we use alpha for angular acceleration. So angular acceleration is equal to angular displacement over time change. So delta omega over delta t. So angular acceleration is angular velocity change over time change. So the SI unit is units of angular acceleration, which is radian per second divided by second. So radian per second or radian per second square. Okay, so in this slide it shows we use x for displacement, a for acceleration, v for velocity, final velocity, initial velocity v naught, and the time. So we already talked about the relationships between velocity, acceleration, and time, displacement, velocity, and time, velocity, acceleration, and displacement, initial velocity, acceleration, and time. So we're going to use similar equations. We just talk about velocity. So angular velocity, we use a different notation, and acceleration, we use uh, another notation, alpha, we use omega naught, alpha, t, and angular displacement, we use theta, f, omega naught plus omega times t. So in this slide, it shows uh, the similar kinematic equations for angular motion. This slide is sort of a summary slide. It shows the variables we use for linear motion and angular motion. So for example, displacement, in linear motion we use x, and for displacement, change of angle, we use theta for rotational motion. And initial velocity, we always use 0 for initial, so v for velocity in linear case, and initial again 0 for initial, and omega for rotational or angular velocity. Final velocity, we just use v for linear motion and omega for angular motion, angular velocity. And acceleration, we use a for acceleration in linear motion, and we use alpha for acceleration in rotational motion. Time t we use for both cases, and these are the equations for linear motion and rotational motion. So you have to have a good understanding of each variable, initial and final, and acceleration, and also the velocity. Okay, now we're going to derive an equation for tangential velocity or speed. So in linear case, we use uh, V for linear velocity. We didn't use a special character for speed, but normally we use S for speed. This is for linear case. So if an object on a rotation around the axis, and if you draw a tangent to that point, this is tangential velocity, T for tangential, uh, italic V for speed, and velocity. Velocity we keep changing because even if you maintain the magnitude constant, we keep changing the direction. Therefore, tangential velocity always change, but we can keep the tangential speed constant if we, because speed doesn't have a direction. So we're going to derive an equation for tangential speed. So we already derive an equation for angular speed theta in terms of angular velocities and change of angle. This is a linear tangential velocity. Okay, so velocity or speed is distance over time. Okay, so if you consider a very small distance, let's say the distance is s, therefore s over t. So this s, which is arc length, it's a small section of this circle. This arc length we can write in terms of radius and the angle, which is equal to r times theta divided by t. So r theta over t. So if you write theta out over t in a parenthesis, we know angle over time is omega, which is angular speed. So therefore, if we put omega instead of theta over t, therefore tangential velocity is r omega. Tangential velocity or tangential speed is r omega, and the units is same as change of angle divided by time, radian per second. Similarly, we can derive a equation for tangential acceleration in terms of tangential velocity before and after, tangential speed vt naught. So velocity change over time. Velocity we know radius times angular velocity. This is linear velocity or tangential velocity. This is so omega is rotational speed or velocity. So Vt is r omega, Vt naught, r omega naught. So minus t time. So r is common, so therefore you can take it out. Omega minus omega naught over t. Omega minus omega naught t is equal to alpha. It's a rotational acceleration. So at is r alpha. Linear acceleration, tangential acceleration is equal to radius times rotational acceleration. This is a relationship between angular variables and tangential variables. So linear acceleration or tangential acceleration is equal to radius times rotational acceleration.